Hello viewers and welcome to a new STM32 World tutorial video. Now this video I will make a tutorial video. A few weeks ago I ordered a relay board. It's a small board I designed with 16 relays and an embedded STM32 STM32 MCU. Now this video is being recorded on a Saturday. I received these boards and did an unboxing video last Monday, so now 5 days ago, and I ordered it a week before on the Monday before. So it's about 2 weeks into the process. Now I made a page on the STM32 wiki where I described this board. It's a work in progress, but it is getting there. And I have linked the videos, both the expectation video, which I posted just after I ordered it, but before I received it, and the unboxing video. So this will be the third video in that relay board series, showing the result of this board. Now, I mentioned in the unboxing video that I made 2 of these boards fully mounted, and I had 5 PCBs, so I have some spare PCBs, which I will never ever use. But the board itself, where are we here? Here I have the board, and I think just to keep the same angle all the time. So yeah, the board is described in quite a lot of detail in the previous videos, and the idea is that it can be powered and run standalone, but it can also be hooked up via USB, and if it is hooked up with USB, this board should, at least in theory, that's part of what we need to test, be able to run powered strictly only from the MCU, and then you have a programming header there where we can hook up an ST-Link device, and that's about it. Let me categorically state right now that I actually think this might be one of the more important videos I have done on this channel, because like a vast majority of projects that need an embedded MCU are relatively simple. I mean, you don't have to make them very advanced. You have to have some process that you need to repeat often, and an MCU is by far the easiest way to do this. So this board makes sense. Let's look at the board hooked up. So right here I have it, where are we? So I have the board hooked up there. I need to adjust that a little bit. There we go. So you can see here on the video that there is a USB hooked up to it, and there is a programming header hooked up to it, and then it is placed so I can see there's nothing hooked up to the relays. So after I received this board, I started reviewing it, and the first review you will do on any board is a visual inspection of the board, and it mostly passed, but there was one thing I discovered, and that is actually there. You can't see that on the video, I'm sure, but the boot and reset labels are switched. So that was the failure of the visual inspection. I have made a test report down here. So now the very first thing to test is whether that's a visual inspection. After the visual inspection, the first thing to test is whether it can go into the bootloader. So let's look at the demask, and let's while doing them right, let me put the device up as well here. So let me reset it into bootloader, and you will see here on the output, it goes into the STM32 bootloader. So in other words, power from USB works, and at least at 3.3 volt, and the USB communication is working, that we can see here. Now, this brings us to the first one. In my review, I mentioned that, let's actually fire up. No, that will not show us anything, but what happened was that I have an enable pin on the 5 volt power supply, and that pin was left floating. And that actually have a peculiar side effect. If you look at the video now, and let's try to make that big here, you will see that there is a green light up. That is the 3 volt power supply, but there's a LED under the 5 volt power supply as well, and that one is off. So right now the 5 volt power supply is off, but now comes the funny thing. Let's see if I can do this. If I touch that header up here, you'll see that I can actually switch on the 5 volt power supply just by touching this. Now, that is obviously because this is a high impedance input, so the electrostatic field from my fingers will actually immediately be enough to switch that power supply on. So that is number 2 down in my, no, it's not, it's later, it's here. So I listed this as a fail or pass, because we understand what is going on. Now, one of the things I mentioned in the last video, which is this one, KiCad 6 it was called, is that I was unsure about whether 5 volt could actually be generated from USB, because the USB goes in through a Schottky diode, so it drops down to about 4.5 volt roughly, I assumed, and then that 5 volt, 4.5 volt will then have to go to the switch mode power supply, and it can definitely not do 5 volt, but I expected maybe 4.2, 4.3. So let's look at the numbers actually as a result of this. Now we went the bootloader, 3 volt supply on USB pass. VBus, if I measure that, is nearly 4.9 volt on my desktop computer where this is hooked up. Same computer I'm using to record this video. So VN being dropped over the Schottky diode ends up at almost 4.5 volt, and the 3.3 volt rail is 3.4 volt. I assume that's my voltage divider that is not entirely precise, or it is the feedback resistors voltage divider that is off by a little bit, but 3.4 volt is fine. STM32, just for the record, can run up to about 4 volt. Above 4 volt, you will start having a problem. So we are well within the spec of that. More interesting though is that the 5 volt supply on USB measures 4.3 volts. So it is more or less exactly as expected. From the VN of 4.47 volt, it managed to generate 4.3 volt stable output, which is more than enough, I suspected, to drive the relays. Now, the 5 volt enable pin that I have listed as a fail, I already talked about that, because it is left dangling. Next step up, can we program this thing? And as you can see on the video, I actually have hooked up a programmer. So let's go down here and let's try to run STinfo-probe and see how does this identify. Remember, I am using the Chinese market only STM32F402, which, as has been documented in plenty of earlier video, for all intents and purposes is a relabeled STM32F401. So I expect to see a ST-Link programmer with a STM32F401. So let's run that, and what would you know? It actually shows up as an STM32F401 something. It's a CB. So that's about it. It has 256 kilobyte of flash, and it's got 65 kilobyte of RAM, which is, and this is why I picked this one, this MCU is cheaper than an F103, and it's got like 3-4 times the amount of RAM. I think the 103's got about 20 kilobyte or thereabout. So it's much more powerful and cheaper. So that's pretty much it. We have already covered the boot, and that's it. So now it's time to actually start looking at what this MCU can do. So I have made a project in STM32CubeMX IDE, and this project is, I should say, quite silly, and it would never be like this. This is just a project I made to test this relay board, and I have enabled everything there is. Now, while we have that, let's fire up KiCad as well, and let's go in and look at the schematic. Now, when I described this board in the previous video, there are a number of things in this board that will probably never be used, but footprints are free, so I put it on anyway. First of all, the MCU is centered around being able to control the relays via this GPIO expander, the AW2523. This GPIO expander was the one I used in my LED board a while back. Go look that up, I2C LED board, where I use this one, have the functionality that it can drive LEDs directly and dim the LEDs, so it's a quite clever GPIO expander. But today I'm using it as a GPIO expander, and that is about all there is. There's a couple of other things on this board that may never be used. There's an SPI flash. This is a 16 megabyte that has also been described in an earlier video, so go back and look at that. And on this flash, I am running a file system called LittleFS. Now, you could, in theory, run FatFS on this, but FatFS, the problem is it's got some sectors, the FAT, file allocation table, that get updated all the time. And these flash, you will wear them down fairly quickly if you're running FatFS on it. So what you need on a chip like this, a flash chip like this, is you need a wear level, a so-called wear leveling file system. That means that it never writes to the same sector all the time. It keeps moving across the chip, so all the parts of the flash will be used equally. So I'm running LittleFS. It also takes way less memory. I'm running LittleFS on this flash chip, but I also have an SD card folder, and if you look closely, you can see that there is actually an SD card inserted in that. This will be tested as well. So in this video, we are going to run through the tests of every aspect of this board. The important ones being up here, can I toggle the PSU, the 5 volt relay board PSU, can I toggle that on and off? Number 2 test, can I communicate with the GPIO expander using I2C? Can I then control the outputs on this? Can I read and write files by LittleFS on this SPI flash? Can I read and write files on the SD card using SDIO? So And finally, can I, well, the two extra steps that I went through testing is, of course, can I control the relays? Can I run all relays um, on without exhausting the power supply when I'm powering it from USB? And the final thing I want to test is, can I actually control these relay by some protocol on USB? So this is what will be covered in the rest of this video. So let's move forward and look at the code. I'm not going to write this code from scratch. That would be insane. That would take a long time. But let's look at the first of all the CubeMX setup. Most of this is, of course, dictated by the schematic, because that would dictate all the pins and how they are connected. So let's see what we have here. First of all, we have the usual, we have a relay, we have a button, which on this particular board is the same button as boot 0. So that one is actually linked down there. I haven't tested that, but I'm not going to use it. We have I2C up here. We have a pin called RSTN, which, looking at the schematic, go straight to the reset pin of that GPIO expander. So I can switch the GPIO expander on and off with that. We also have I2C3, which goes straight out to a header. Let's look at the schematic. We have it up here. I call it I2C2, but it's actually I2C3. So that is kind of wrong. But it goes straight out to a header that is intended to actually probably operate as a slave, so it can be controlled from an external source of something and then act as a slave if I want to do that. But I can also go straight into the I2C port, so that's not probably never going to be used, but well, I had the pins, so why not? I have the SVO pin out to my programming header. I have the STIO, which goes over to the actually, wait, let me remove that one. It's getting in the way. I have SD detect pin. I have the programming pins, SV clock, SV. I have the USB pins going down to the USB header. I have the UART, which goes to the ST-Link, and I have the SPI down here, which goes to the flash. I have a LED on board. I have that enable 5-volt pin. So that is about it. So let's look at the GPIO. So you will see here that the enable pin for the 5-volt is low, GPIO level low. So the moment this firmware is in the MCU, it will start up, and within less than a millisecond it will yank that 5-volt low, meaning that the problem with that being floating is no longer a problem. It will only float for less than a millisecond, I'm sure, microseconds. So it should not be a problem, and indeed it isn't. So that is pretty much the setup here. So let's look at the code. Now, the code itself I have included, and these have been introduced, all of them, in earlier videos. So I have my W24Q128 library, which was introduced in an earlier video. I have my AW9523, which was included in an earlier video. It even have the LED demos, which I'm not using in this case because I'm not using it as a LED driver. I have added LittleFS, which I don't think I made a video on, or I have not made a video on yet. But it's got FatFS, and of course that is configured down here in CubeMX to run on the SD card, and the STIO, just to cover that, is running 4-bit wide bus. So all of that has been covered extensively in earlier videos. So go back and watch those. So I'm including, so let's see what happens when you start up down here. I have some animation with the relays defined up here. I'll show you that later, how that works. But let's look at the startup code here. We initialize all this stuff. Oh, an interesting thing I wanted to say is that, of course, you would never have the LittleFS on FAT and FatFS on an SD card. You'll probably pick one or the other. But I just wanted to see what happened if you enabled everything to test it. And you see, we end up using 74 kilobyte of flash. That is settings optimized. That is with debug optimization, so I can actually make it smaller if I want to, which is about 29% of the flash that I have used for this. Had this been an STM32F 103C8, I would already have been out of flash, so it wouldn't have been possible. But with this Chinese market only F402/401, it is indeed possible. I have plenty of flash to play around with. So what am I doing? I print out a statement, relay board starting, and then I go straight on to test that W24Q128, which is a 16 megabyte flash chip I have here. So I initialize it. If the initialization work, I fire up LittleFS on that chip, and then I keep track of the boot count. So I will have a boot count variable here that is set to 0. I will try to open this file on LittleFS. If that works, I'll read the value of that into the boot count. I will then add 1 to the boot count and write that straight back to the file and close it. So I have a file on the flash chip which keep track of the boot count of this. Then I'll print that out. Then I'll check the LittleFS speed. That one is defined, where were we? LittleFS speed. I have made an LFS util. Nope, sorry, it's in my core source LittleFS. So I have a test procedure in here, LittleFS speed, which will basically make a 1 kilobyte buffer and then fill that buffer up with values, and then it will check my UV tech, and I'll write 100 of those down to a file. That's 100 kilobyte I write down. I'll then close the file, I'll open the file, and then I'll read that back and close the file again and print out the timing of that. So that is the LittleFS test, which is being done on startup. Then I'll do the same with the microSD. I will mount the microFS. I'll do an LS, print out the files that are on that FatFS, and then I'll check out the FatFS speed. That one is defined up in this FatFS support here, and you have LS there, and it will take a whole megabyte. It will write 1024 of these 1 kilo buffer down to a file. Am I reading it again? No, I'm just checking right. It's not that important. If I can write, I can read it. Then I initialize the AW, the GPIO expander, and it is noticeable that, remember, the N5 volt is pulled low, so it needs to go on, and I only set that on after I initialized, and then I'll set all the relays to 0. That's it. Oh, they are default 0 anyway, so this is actually probably a wasted effort, but I'll probably come back to that later. So that is about it. So let's try to run this and see what happens and analyze the output slightly. So where are we? I want this one. I'll run my microcom. It is running, as you can see. This is, of course, this one. You can see it flashes and it prints out. I've done that exercise. Now, it is not necessary, but if I have a spare LED, I will usually just let it blink. And the reason I do that blink because it's give me a quick visual. If I somehow manage to crash this, it'll stop blinking. Oh, something is wrong, and I will have to fire up probably the debugger to see what is wrong. So anyway, let's try to run this. There, going. So now it's in the loop. So let's look at what it actually writes over here, what happened during. So you can see it's testing the the flash. Boot count is currently 333, so I have flashed this 333 times. Let's start by actually verifying that works. Let's try to flash it again. So now it should be 334, and you can see it is now 335. So that's it. Writing 100 kilobyte down to that flash memory using SPI takes 1.6 seconds. Reading it back takes 0.2 seconds, and removing the files took 5 seconds. So that's pretty much the speed of the flash chip. Then I am mounting the SD card and I'm testing that. You can see I actually have some WAV files that goes back. I probably used this SD card in my music player that I made a while back. It also have an uptime which I'm not using yet, but that's all leftovers from that one. But it's got that big dad, which is not big dad, but big dot dat, which is the ones I'm actually writing. So writing 1 megabyte takes 0.6 seconds, which is pretty much matching the values we got in the earlier video when I was testing this stuff. So all good, all good. Now, the final thing that is worth testing is you can see here actually there that it showed up. Let's reset it. There, it shows up as a HID hit device, identifying itself as an STM32 world relay board. Now, I have on this system, we can look at it here, connectivity. I have enabled the USB port, and more importantly, down here in my USB device, I have set it to custom human interface device class HID. This is where I have set the descriptor. I have tweaked this a little. I am using out report of 8 byte. That means I can receive 8 byte at the time, and then well, I'm not going to go into details, but I am probably going to make a video about this, how to create this. And if we look into the code briefly, let me get rid of that so it doesn't block. I am learning, see? The important part in my main here is up here. I end up, when I receive data over the HID, it ends up here. I'll print out the first 3 bytes I received, and I will set the relays to that. Actually, forget this and let me test something else first, because I actually made a way where I can have these 16-bit values that I'm representing here binary, and we can say down here we can set an animation interval of 1,000, and then down in the main loop I can enable that animation. So let's get the device back up. Let's see the output, and let's try to flash that. So this is kind of my first test of the relays. And there we go. You can see up in the corner, you can see that it toggles one relay on at the time, and then it moves on and toggle the next relay, and so on. It goes around that semicircle, and every single relay can be toggled. I have some, you could up here set this to go a bit quicker by setting 100 milliseconds interval. Now you should see that go much quicker. I don't know if you can hear the relays. I can hear them clearly, but yeah, so that works. Now remember I mentioned, I don't know what happens if you switch all the relays on at the same time. So let's add a little more brutal test here. I do a 0101 or a 1010 pattern all throughout, and then at the end I go and I toggle all the relays on, and so on and so forth. I'll do that every 100 milliseconds. So let's try to run that. Again, I'm not sure whether that goes through the noise cancellation and noise filtering, but you might be able to hear the relays. I don't know if that's possible, but I'll have to check that later. So anyway, let's leave that there. Let's go down in the main loop and let's disable that animation thingy. Now I tested, I can run the relays. I can run all of the relays at the same time without killing the power supply. Now let's look at what I was about to explain before. So when I receive data over the HID, it will end up in here, and I simply use those, not the first, but those 2 bytes. I use that to set the relay, and that is all I'm doing. So let's try to fire this up to run that. Now it should switch off. It should not run the animation. It should switch off all the relays, but it should switch on the 5-volt power supply, and it came on there. So now the board is powered, and it's got USB. It shows up as a HID device on the USB, and the loop is running. So I have a utility I found and I compiled, which is called HID API tester, which can be used to test from my command line. Actually, let's flip these around so I don't cover this up. So it will basically take the ID of the board, it will open, it will send 3 bytes, and it will send 3 FF00. So this one should switch on 8 of the relays while switching off. So if we look at the board as it shows right, I'm not good at this, up there, you will see it should switch on all the high end, the ones on the left hand on that picture, and leave all on the right hand off. So let's try to run that. There. And you see immediately it switched on those relays. Now we can flip this and say, well, I want to switch those relays off, but switch the other 8 relays on. And we run that, and it is immediately updated. So now we have a USB. We can control these 16 relays from a USB, and I actually did wait, source test reg f. So I did a relay test, small shell script, and all I'm doing is I keep running that and send different relay patterns out to it. So let's try to run that relay test. That's pretty much what before I did internally, but I can now control this relay board via USB with no problems at all. Yep, so that works nicely. It could also, I'm not going to test this, but it could also be, we could use a UART to control this, or the I2C, but I know that will work, but I can't be bothered actually developing it right now. So that's pretty much all physical test. Now, I am going to do a little sidestep now, because now when I make a board like this, I don't expect it to be perfect. There is almost always something you overlook, and that's the reason you make prototypes. But in this particular case, I have a very, very, very annoying thing with this board. As you remember from the unboxing video, I made two of these boards. Now, one of those is the one you see here, and it works flawlessly. The other one I have here. And, well, what can I say? It doesn't work. What is not working on this board is the 3-volt power supply. Now, when you plug this one into USB or external power, but USB, the 3-volt power supply, which should always come up, is not coming on. However, if you plug in a programmer, because the programming header also can supply power to the MCU, the MCU works perfectly, and the 3.3 volt plane is energized on the board, so it can be powered via that, and the 5-volt power supply is actually working flawlessly. Now, let me look at the schematics, and this is why I have no problem with mistakes, and I have no problem with errors, and in this case, I am completely baffled why this is happening, and I haven't worked it out yet. So, well, I mean, if you have any good ideas, comment down below. What I know about it is this: when I measure with the USB, remember USB power only on the VN. No, let me start by saying, since I can power it from the programming header with a little 100 milliamp LDO on the ST-Link device, I know that there is no excessive load or short on the 3.3 volt power rail. It works perfectly. Now what happens is, if I plug it into USB, the USB voltage will drop down. That means that there's an excessive current draw in on this side, and I actually measure that current draw by putting up an external power supply. And if I do that, it sucks down, this one will suck down about 400 milliamps. Now, looking at the schematic, I have measured everything. I have measured the connections, I have measured whatever I can measure in circuit, and there are nowhere that can go except internally in this one. So I was kind of in my head assuming, oh, I got a broken LMR 3364, but I don't, because, let me make myself bigger, I actually had some prototype boards I was made a while ago, and this prototype board, where is it? Over here. It's got 3 of these power supplies, because it's got a 3.3 volt, and it's got a 5 volt, and it's got a 12 volt power supply using exactly the same design. And I don't know if you can see it. I have actually, so I have removed the LMR, and also the inductor. I have removed that from here and transplanted over on this board. A little fun story, by the way. I do have a heat gun but I'm not very good at using it. So it was much quicker for me to pop down. I live nearby an electronic, they sell mobile phones, and there's a lot of shops that repair mobile phones, and a lot of those shops have a heat gun. And I went down there and I found a Pakistani, very nice Pakistani guy that was very good at using the gun, and he did it for me. I couldn't be bothered, but he did a very good job. So I have actually replaced that LMR33640. Uh, I have replaced it, uh, and I have also replaced. He did that. I didn't think there was anything wrong with the coil, but he did that, and it is still not working. It is not coming on. Uh, it must, I guess, be a PCB issue. But I measured all the connection, and I know there's no shorts. So yeah, at the moment I'm baffled. But on one of the boards, it didn't work. On the other board, it works perfectly. Now the problem of if I had made 5 of these boards, if I have fully populated all 5, I would probably have felt better, right? Because if 3 or 4 of them failed, then I have a problem. I have done something wrong. If one was failing out of 5, I'm willing to put this down to a fluke, a bad capacitor, some dirt under the short, under the MCU, or under the IC or whatever. I would be willing, but with a sample of, with only 2 samples and a failure rate of 50%, I'm none the wiser, and I don't like not to be wise. So, well, I might have to run some more of these at some point, or I'm considering ripping this out and actually make that a standalone board. I was thinking about taking this exactly as it is here, but replace this resistor with a trimmer. That would give me a neat little adjustable PSU, which could take anything. I mean, what I love about this one is that it will take input from half a volt above what you would like to get out of it, and up to 36 volt, and it actually exists in a 65 volt version as well. He'll just, so you can basically put whatever you have into it, and then with the little trimmer you could adjust exactly what do you want out of this. And I might actually make 10 of those just to have it lying around in a drawer whenever I need a power supply. And by putting a trimmer, I will be able to make odd voltages if I want to sort of slightly over voltage something, or the other way around. Just for test purposes, it's probably, and I might want to do that just to test, because I need my sanity back. I need to figure out what went wrong with this. So that is essentially the result of my testing on this. I am still working on it, and I think on the relay board I mentioned down here the mystery fail. I did mention this. I can't do it here where I'm recording this video, but I actually did test the relays. Remember, it was spec'd to 2 amps per relay, and I did that using my bench PSU here, where I set it to 12 volt, no, 24 volt, and 2 amp current limited, and had that running while I was making dinner and eating dinner. So it was running for hours, and it didn't even get warm. So the cable, probably in this case, because of the setup, the cables will get warm before I'm pretty positive I could have run the 24 volt and set this to current limit at 5 amps, and it would still have been fine. So that's not it. I have mentioned the mystery fail down here. Uh, and as I say, if anybody have any idea, please put them in the comment bar below. I am quite baffled about this failure, because I think this Now, it is a little compact the way I did this up here, but it is quite easy. I mean, I can test that the input is not shorted anywhere except where it is supposed to be shorted. I can check that the feedback circuitry is running. There's no real dangerous stuff down here. Now, one thing it could be I'm doing this, which is not according to Texas specification, but that is for the power good signal. The power good signal is up here, and that is an open drain. So what they do is they basically take the VCC output down here. But if you don't use the power good signal, which I don't, then this one doesn't matter at all. It doesn't do anything. So yeah, I don't know. What we're looking at here, by the way, is the new version with the bum 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 here, slightly different inductor. The Coilcraft, as you saw, is actually those Coilcraft inductors who are about $2.80 each. This one is 10 cents. So yes, I'll have to test it with the cheaper one. I mentioned that I actually flipped these two silk screen. The boot and the reset was flipped around. Remember I had this touch thingy, the one floating up here. I have moved that down because it's going down to the MCU anyway. So I put that down there with a pull down resistor, so it needs to be actively driven high from this one to enable the 5 volt. I've already fixed that. So pretty much I've fixed everything on this version that needs fixing, um, which wasn't much because it was actually working pretty good. As well, oh, I have also this one was a three-way jumper before. I changed that to a pull down resistor, and then these two will go up to one. Oh, I even left a bit of silk screen, um, which shouldn't be there. There, remove that one and that one. Okay, so yeah, it there might be a new version if I want to test my power supply, but the big mystery is that power supply that doesn't work on one board. And it's not like it's I have had the other board running for days now. I have booted it more than 300 times. It's just working. It's no issue at all. This one I replaced the two most central components. It's still not working. So I don't know. So that is about it as usual. If you like this video, please do like and subscribe. If you don't like the video, and I know I'm long-winded, but that's part of the charm of this channel. If you don't like it, please let me know why. I might not necessarily change because you say so, but at least I'll know what people are thinking. I gotta admit, running a YouTube channel, the one thing that annoys me are people that just click down without letting me know why, because it's sort of a pointless exercise. It doesn't teach me anything. Well, I mean, okay, if it makes you feel better, what can I do? As usual, have a wonderful rest of the day.